Okay. I don't think I have any on me. Do you have lab or can you come by lab today?
What time?
1:30. Or 1:30 to 4:20 to get papers. You guys are killing me.
Yeah, sure.
Yeah. Hmm? Uh,
Is this Thursday? Is that going to be on chapter 3?
Probably more like chapter 2-ish focus and some of chapter 3.
Yes. Okay, thank you.
Can you do it before 1:30? Or what time is it? 1:30?
I mean, class ends close to 1, and then we can go up to my office and get it right after. But that's as fast as I can move, basically.
Okay.
Maybe I can get it during break, but no guarantees, okay?
Okay.
Running out of physical time. No. me. Yeah. All right, welcome, welcome. I actually have the stream running today. Remembered to hit go, and we have a lot of people joining us there live, so welcome, and thank you all for being here in class. Couple of things real quick. So of course, let's make an announcement tab. So announcements, oops, if I could spell. So don't forget your reading quizzes. So I looked over the weekend and there were a few blank reading quizzes. So make sure you do those, catch up on those ASAP. And then, right, the other thing is I'll emphasize, especially as we're still kind of, getting into it, so don't give up and ask questions. And I mainly saw this in my Chem 104 class where everybody was really confused, but then once lecture ended, everybody also ran out and nobody was asking me or setting up appointments, right? So I know, especially kind of the way your book covers this beginning material is a little all over the place. It seems to kind of expect you to pull background knowledge or just kind of the depth that it goes into. But again, just ask questions, right? We're trying to get everyone up to speed. So just, right, don't give up. Chemistry is obviously inherently hard. And then, so this is the last week where I'll be lenient on PPE. So if you saw my announcement, it's the paper lab where we'll kind of, again, explore how the periodic table came to be. And then next week, we'll do the flames. So next week, don't forget your pants and your cotton clothing. All right, so let's continue on. And so again, your book kind of goes into this hodgepodge of materials. And really what it's going for is the reactivity, right? So it's kind of going through a lot of these metals. And so it also likes to compare our halide reactions. And so first, again, we start with the alkali metals and talking about their properties. And so they kind of introduce electron configuration, which we'll get into in just a second. But again, we're trying to pair reactivities, but the problem with your book is it's not necessarily addressing electronic structure at this moment. It's saying, hey, let's look at all these cool reactions and what happens. And so that's kind of, again, the first part. And so we're saying, okay, and this is a good point to put 1+ if we haven't already. So again, we're arriving at the idea that they have one valence electron. We can see that in the electron configuration. Again, we'll come back to what this means later, more in depth. But we can see, okay, they have different energy levels, 1s1 for hydrogen here, and then 2s1 right for lithium. So going down, just adding subsequent onion shells, and all of these again having one valence electron. And so with the alkali metals, it again points out kind of the reactivity, and so we see salts formed in a 1-to-1 ratio. So potassium chloride, right, sodium chloride, sodium fluoride, and just kind of showing, again, the similar reactivities, right? So basically we're saying, okay, well, anything from column 1 tends to, pair with one of these halogens in a 1-to-1 ratio, right? And again, it's just kind of telling you, let's look at those patterns.
Are those fundamentally known as salts?
Yeah, I believe I said that. So, right, again, so these are all just salts. All right, so then moving on, and so now, right, it points out, okay, well, now we have the alkaline earth metals. They have, again, different reactivities. Sorry. And so now we're saying, okay, they have a cation with a 2+ charge. And again, write that on your periodic table if it's not obvious. So 2+. Okay, we're getting into it. So again, 2s2. So we'll kind of, again, revisit that. And so now we're saying, well, all these metals can react in a 1-to-2 ratio. Yeah, question?
What was the definition of alkali metals again?
So there's our definition. And so again, right, we can look at our periodic table. We have magnesium, calcium, strontium, barium, and they all react similarly. So we can have, and so again, emphasizing, so strontium chloride with 2 chlorines, right? We would expect, so magnesium could do the same, magnesium bromide, right, etc. So we can look at this, so predict any of these analogous compounds. So on and on and on. And so it also mentions how, of course, again, the alkali metals are known for being super reactive with water, and then the alkaline earth are not as reactive. And so let's see if we have some equations here. And so we're looking at, again, so now we can start practicing, again, our ratios. And so we could examine it for calcium and oxygen as well, so how they react. And so this is also practicing our balancing equations. And so now if we go to oxygen, so now oxygen, we know that it reacts and makes a -2 oxidation state. Right, so we can write halogens, -1. Oxygen, and again, so what we're taking away with our reactions is the ratio, and so we saw for these, so calcium and oxygen can react in a 1-to-1 ratio there. So again, reflective of that 2+ and 2-. What other good reactions? And so then we can look at our other parts of our periodic table. And so, of course, most of our elements are metallic. We have our transition metals all down here in the middle. So again, we'll kind of look at its electron configuration. And then our metalloids, remember, our stair step, so our semiconductors, and then non-metals over here, so main group. And so just looking at some of the behaviors. So the metalloids, there's a lot of cool chemistry going on with metalloids. So this is kind of also known as main group chemistry. And so people try to do kind of cool stuff with this. Part of why that is it's kind of semi-metallic. And with that, right, we're trying to do basically redox chemistry, which again, I don't know what that is, but basically transferring electrons. And so what's really cool is even though, right, they're not transition metals, they can still transfer electrons and kind of help do catalytic processes, or at least that's the goal of the research. And so now just kind of, again, looking at our properties of our nonmetals. So of course, they're in the upper right side of our periodic table. Again, yeah, so hydrogen is the exception over there. We'll, again, kind of talk about hydrogen because it does do some cool, funky stuff. And so, again, most of our nonmetals are over there. And so what we want to take away is our nonmetals form anions. So that means that they accept electrons. So we're going to, again, start seeing this concept with how they fulfill their octet, which we're still kind of dancing around. And so again, we see that with the halides. And we're starting to see that they do this 1-, and right, oxygen and everything in its group is 2-. Yeah, so halide is just in the salt form. And so back to our halogens. So I think we've looked at them. Have we looked at like kind of the pictures on Wikipedia at least of the halogens in here? Okay, I see some, yes. I get my classes mixed up. And so, right, if we remember, so fluorine was that gas. Chlorine's also a gas, bromine's a liquid, and iodine's a solid. And so, again, what we were seeing was their reactivity with metals. And so a lot of metal compounds. And so we can look at, let's just talk about some other ones, some fun reactions. Also, there's a typo on this periodic table. Notice these should all be 2+. So 2+. And so we look at, let's take a look at aluminum for a second. So aluminum, I guess we'll show this video. I was debating whether to pull it up. Ah. Okay, let's try this one. And so this is, I'm not sure that you would actually synthesize it this way. But this reaction that we're about to look at is a synthesis reaction. And so it's just aluminum metal plus liquid bromine here. And it's going to give us aluminum tribromide. And so let's just look at this reaction. It's just nice and impressive. Hang on. Bromine. So you can see already that it's a liquid, but it's an angry fuming liquid. So this would have to be done in a fume hood. Yeah, so that's toxic when you see that iodine. It's a bad thing. And so that's just aluminum foil that they have. And there it goes. All right, so that was nice and fun. And so again, part of what your book is doing is showing you similar reactivities. Yeah.
Why is it sometimes called aluminum and sometimes called aluminium?
Differences in pronunciation. I won't argue over what. I think aluminium is technically correct, but yeah. But all that's to say, again, we're just seeing what ratios that they form in. And so aluminum, right, is 3 plus. And so that means 3 equivalents of bromine will react.
That's weird because you could like separate them and redo the experiment. It's not a good idea. Why would you guys?
What do you mean?
Like you start it on fire or whatever.
Yeah, so when it's like on fire reacting, like that's it explosively making aluminum bromide. And so what I was kind of saying too is like, I don't think that that's actually how they make it on an industrial scale. And so why I say that is, you know, obviously it's spectacular, but aluminum bromide, and we can talk about this. And a quick question in the chat, how do we know it's a synthesis reaction? So synthesis is just when two things come together to make one big thing. I think we had asked about that. Does that ever happen? And so we're looking at a few of those reactions. And so your book is also like, okay, well, predict, right? So then, and let's balance this for good measure, right? So again, just kind of doing swapping my variables. Okay, balanced equation, always good. But then, you know, your book says, well, predict then what happens if we react, you know, aluminum with fluorine. And well, just again, based off of the fact that these are both halogens, we would expect probably a similar reaction. We could make predictions. So then your book starts saying, like, maybe you can even, you know, kind of make predictions on the reactivity. So just like we saw, again, with our alkali metals that increase reactivity as we go down. So it mentions, right, that rubidium and cesium are so reactive, they're in ampules. But it's saying, right, we can kind of predict reactivity. And so with the halogens, you know, fluorine probably tends to be way more reactive. And so we can maybe predict, like, it might be more explosive potentially. So that's also kind of what your book's getting at. And so again, right, we would assume they would make the same compound. So 2 equivalents of aluminum trifluoride. And so again, similar patterns, right? And so that also means a whole family of all these compounds exists, right? So that means boron probably reacts in the same way. So, right, there's probably boron trichloride, which there is. So let's look at it, right? And so there's aluminum iodide. And so all these things, though, are hygroscopic. And so aluminum iodide is probably going to be your most stable. And where did my tab go? For aluminum bromide. So again, let's just look at the picture. It's not that remarkable on the Wikipedia picture. So it just kind of looks like this whitish, grayish powder. But if you were to open one, so especially, so I've worked with aluminum chloride. So let's just pull it up. Again, it looks about the same as all the other halogens. So again, somewhat unremarkable, white powder. But if you look at it, and you kind of open it, especially an older sample, it's going to be kind of weird. It might have some HCl in there because it's been reacting, with the water in the atmosphere. So there could be some aluminum oxide. So yeah, these samples can degrade over time. And yes, they do kind of react. And it mentions again how they're hygroscopic, so they are going to be kind of sucking in water. And so again, that's just giving you kind of reactivity. So let's take a moment to talk about hydrogen for a second. And I think it came up in your homework as well. And so the funny thing about hydrogen, so again, hydrogen's kind of over here, but it sometimes almost acts as like a halogen. And when it does this, it's in its hydride form. And so it can make all these metal hydrides. So hydrogen makes metal hydrides. And so it can essentially act as, again, kind of H minus here. So we could have aluminum hydride, and again, similar to just kind of aluminum trichloride. So they're similar, right, but obviously different. So of course, hydrogen obviously just has one electron. And then let's look at some other compounds. So this is a fun one. So lithium aluminum hydride is a good reagent. It's a reducing agent, so it's a nice source of H2. But as you can read in the first sentence here, so it's pretty reactive towards water and air. And so this is the cause of a lot of fires in a practical chemist experience. And so usually how it happens is you have a little bit of this residual powder. And again, you can appreciate how this hydrogen is attached to the aluminum here and attached. And then you expose it to air. So usually you're like taking your CHEM wipes out of your glove box, and then your trash lights on fire because of this residual amount of lithium. And so there's been plenty of trash fires due to litho. But plenty of other metal hydrides. So let's see. We can pull up. Oh, geez. Yeah, so probably the other more common hydrides would be magnesium hydride, and well, we'll put lithium aluminum hydride and draw that out. So aluminum. And so now this is kind of getting into polyatomics, or starting to. So aluminum is a 3+ charge. We say hydrogen's -1 when it's a hydride. Again, only when it's attached to metal. Yeah.
Are you saying generally metal hydrides tend to be very reactive?
Yeah, they tend to be pretty reactive, or they're also used for like hydrogen storage. So there's like a whole research vein because, trying to use hydrogen as fuel. So we kind of saw that with the balloon, right? So the problem with the balloon is the hydrogen was leaking out right away. And so to kind of get around that, obviously if we can't pipe hydrogen around like we do fuel, what if we could do it in like metal hydride storage or something like that? So that's, yeah, where the research comes in. And let me finish this thought before I answer your question. So right, aluminum's 3+, hydrogen, we said when they're these hydrides, again, when they're attached to a metal, -1, and so now we have a 3+ and a -1, so this is overall with a negative charge, which explains why that lithium is hanging out there. Right, question?
Do metals become, or do elements become less reactive as they get heavier?
What do you mean heavy or?
Like, when you get further along the periodic table, it seems like metals become less reactive than others.
I mean, that's not necessarily true, and it like depends what we mean by reactive, and yeah. All right, so back to where we're at, or at least hodgepodge of information. And so let's at least start going through our electron configuration. So we do want to start to understand that. And so let's look at our electron configuration. And actually, let's pull up our P table. And so if we go to our P table, we can click our electrons. And so what's nice is they have all our potential energy levels here. And so do we understand what this is saying at all? Yes. So various blocks, but not just that, because, right, essentially, and so we're kind of getting into that with chapter 4. Yeah, what do you? Yeah, so right, that's what we want to get to is the shells. And so that's kind of like where we're dancing towards, but I feel like it's hard for y'all to maybe follow sometimes because the book's like, hey, look at all these reactions. But yes, what we're trying to do is understand, all the energy levels and why do they react in this manner. And so let's kind of at least start off with kind of, what this is. So this is all derived too from quantum mechanics, right? And so it starts with trying to just solve the Schrodinger equation for hydrogen and then solving probability density maps. And so all we need to appreciate is, right, the pretty pictures that come from that and saying like, yes, these are where the electrons are. And so the first thing that we notice is we always start filling in our electrons, right, at the lowest energy level. So that's just, basic thermodynamics, whatever is more energetically favorable, right? You want to put it in the lowest energy level. And so that always starts at the 1s. And so we start at the bottom. And again, kind of how this course is taught is we kind of bounce around with orbitals. But we can at least start with that. And let's actually take even a zoom out for a second, because maybe you are familiar with the Bohr model. And let's make the connection. So, right, the Bohr model in school, you kind of have this oversimplified onion ring of like 2, 8, 18, and then like 32 or 36 or something. 1, 2. Sorry, I was trying to do some math. 4, so 16, so yeah, 32. Right, so we have something oversimplified like that. And so we're trying to recorrelate these. So now what we're saying, so this is our n equals 1 energy level. And so by quantum mechanics, it can only have an s orbital allowed. So that's where that little 2 comes from. So we have our 1s. And so our s orbital is just a sphere here. And then we can represent it as a little line here with 1s. And then so we fill in our 2 little electrons here, or we can, sorry, kind of got ahead of myself. So this is the max that it can hold. And so I also kind of drew it like this. And so what we're saying is, right, electrons have to have opposite spins. So that's, again, right, from quantum mechanics. So we're saying in our orbital at max, it can have 2 of them, and they're going to be opposite spins, right? So you cannot have that. That's not allowed in the same orbital. That's spin forbidden.
You spin like the actual electron spin.
Yeah, so it's, right, electrons. So this is kind of getting ahead of ourselves, but so electrons have a spin, and it's either called spin up, spin down, so spin plus 1/2 or negative 1/2. And chemists usually just represent that by these little half arrows there. All right, so there's that. And so with our periodic table, and I always have you label this in some funky manner, right? Because it doesn't matter what element we're doing, we're always going to start at the top. And so this top here corresponds to our 1s. And so, right, that's why our hydrogen is 1s1, as it fills in just our s orbital. We could write out, so now hydrogen, we have our electron configuration, so 1s1, since again, right, hydrogen just has one electron, that's why we can focus on it. And then we could also write, so this is coming in chapter 4, but we also want to translate this to our Lewis dot structure. And so that one little electron, right, we can write there. And so that's already kind of telling us a lot of information, right? So it's saying, okay, well, this is kind of telling us why it's a diatomic, so it's not really stable, right? You don't really see hydrogen radicals. We can talk about, later the existence of hydrogen radicals in space, but on our Earth, right, it exists as a diatomic.
So that's why it takes an electron, is because it wants to fill that S shell.
Yeah, and so that's filling the S shell, and so now's a good time to say this first little row, when we fill it up, then we can say helium is satisfied by the duet rule. And so, right, most people have probably heard of the octet rule when we have a fulfilled shell, but obviously helium doesn't have p orbitals, so it's happy with 2. And so that's why helium is considered, right, a noble gas still, even though it just has 2. And so, yeah, right, we can move along. So 1s1, and yes, helium's kind of in a funky place here. Maybe this periodic table is more helpful for that, where it puts helium really in the S block, right? So it's clear. And well, let's talk about what does that mean, S block. So S block, now we're just saying any of these elements here, right, they end in a NS1 or NS2 pattern. Again, we can go back to, if I can find it now, our other periodic table with our electron configurations. So write this one, and either write that on your periodic table, right, my NS1, or just kind of highlight it. Okay, they have all the same endings, right? And so that's what we mean by S block. So again, their valence electron, their last electron is in this S block here. And what's also convenient, well, let's say you forget, you're panicking, I can't remember how many electrons are in the S orbital. It's only 2 across. So 2, that's how many are in the S total, 2. All right, so let's keep marching along with filling in our electrons. And so now the next thing that's important to note is, so the biggest energy level gap is from the 2s and the 1s. So that's the biggest. And then each subsequent energy level gap gets smaller and smaller and smaller and smaller and smaller. So that's also why we start seeing kind of funky things.
Does 1s and 2s just correspond to the number of electrons in the S orbital?
So they correspond to the energy level. So now that we're at the 2s starting at lithium, right, if we go back to our Bohr model, if I can find where I put that. So now the 2 corresponds to this n equals 2 here with the 8, right? And so now what we're saying, and this is back to quantum mechanics, so now second energy level. So now the orbitals that are allowed are S and P. And again, we'll do this again in depth. We're just kind of trying to do the electron configuration. But now we have a second onion shell, our 2s, which looks just like our 1s, except it's slightly bigger, right? And so that's all it is. Again, another onion. And then we have our p orbitals. So there's 3 p's. And so we can label them by their axes. So I'd like to put pz as up and down. And they have opposite shading like this. And then py, so that's coming in and out of the plane of the board, at least how I'm drawing it. You can always relabel your axes. And pz. And so the point is that there are 3 of them, and each one of these suborbitals holds 2 as well. So 2 electrons in each right? 6 total. And so let's go back to maybe this periodic table. And so, right, we can start filling across. So, okay, we're at lithium. So we're back at lithium. Okay, alkali metal, right? Again, thinking about all the salts it can make, lithium chloride, lithium fluoride, in that 1-to-1 ratio. Okay, filling in that 2s1. Then beryllium gets its 2s2 shell filled. Okay. Now we go over to boron. And so you should write this maybe on your periodic table if you need to, right? But this is what starts your 2p, right? So your p block starts here, and then you can start filling in your p shell. And so let's kind of take a closer look too at how this is filled as we go along.
When you get to the P shell, after, the beryllium, you go boron. Does it create a third, shell, or does it just add on to the second shell, and then the P shell?
Yeah, so that is, it's filling up the p shell, right? So it's still on the second energy level.
What's in the second energy level?
Yeah, so it's still like just thinking to the basic Bohr model. It's still on the second energy level, but again, now it's like a dumbbell. So it's, in 3D, it's still considered the second energy level, but it's kind of, you have to kind of visualize it in different ways, right? Because you have everything is onion ringing, and so sometimes you have to kind of think about it simply of like, yes, we're on the second energy level, but then, right, it's also where it is, probability density map. Because that's really what this is. All right, so let's look at nitrogen for a second. And so see if you can write the electron configuration for a second.
Do the energy levels on an element correspond to the row?
Kind of, but yeah, I'll note when it does and doesn't. All right, what do we get for nitrogen's electron configuration?
First and S1, or 2 and S1, right?
Yeah, so 1s2
1 S2, then 2 and S2,
and 2,
and that should have 3 and P.
and then 2p3.
Yeah.
All right, so that looks good. And so you can always sanity check, right? Add up your superscripts to make sure that it matches for how many electrons you expect. So 2 plus 2 plus 3 is 7, right? Nitrogen is 7 on our periodic table. It's neutral, so yes, that's what we expect. And so what we want to practice doing is, now that we have this electron configuration, we also want to put it visually, and again, what that looks like with our orbitals. And so we can start sketching that out. And so as we kind of play with these, you'll notice that at some point we'll drop the core. We just kind of, show it when we need to. But I'm showing it now just explicitly. And then we have our 2s, so the next energy level, then 2p. So again, I'm trying to show relative energy levels, so higher energy. And just like, Autumn did a great job writing out the electron configuration. And yes, right, this is again how the electrons fill in. So we start at the bottom, 1, 2. So those are paired, and then s orbital, right, 3, 4. And then this is where, so I think, again, in high school, if you've been exposed to this, it's kind of like the candy rule, where like, oh, every side gets a dot or something. But what they were really trying to get at is, well, these are degenerate orbitals. And what that means is that they're the same energy level. So degenerate, same energy. And so the question, it's not, again, in high school, it's like this little fantasy of like, yay, everybody gets a piece of candy. Well, why that is, though, is because when you pair them, and it's not obvious here, because again, they're just two, you pay an energy price to pair. So there's a little energy price, since those electrons, right, have a little bit of repulsion. So to keep them in the same shell, right, there's a little bit of energy price paid. And so that is why it's unfavorable to pair, right, before distributing to each orbital. So they're all the same energy level. So again, it's more favorable to put one in each subshell first and then go back and pair them. So that's nitrogen. And so then if we compare that to oxygen, so now oxygen, so we can do it, right? It's just the next one over, 1s2, 2s2, 2p4. And so now we can start to pair. And so we can just look at our valence electrons. And so kind of also what we've been getting at, again, with your book giving us trivia, is it's the valence electrons that dictate our reactivity. So oxygen, 6 valence electrons, so 1, 2, 3, 4, 5, and now we can pair that last one with 6 there. Yeah, a question about the energy price. It's just, again, with 2 electrons in holding them in the same shell, that requires electrons because that requires energy because there's a repulsive force.
And this visual is the 1s orbital above the 2p orbital.
No, so I didn't draw it. So that's what I was kind of showing here, right? So the 1s is always the lowest one. I just didn't show it because, right, we're trying to focus on the core.
I saw the one above, and I thought that
Yeah. There we go. And so kind of the other thing that, again, we want to start doing, it's chapter 4 that officially does the Lewis dot structures. But the easiest way to translate this is we can take our valence electrons. And so now looking at these, there's 1, 2, 3, 4 of them. And how many sides are on our atom? 4. And so I like to say that each one of these sides is basically one of these orbitals. It doesn't matter which one. But then I want to draw my dots reflective of that. So again, for our Lewis dot structure for oxygen, I'm going to have 2 pairs of dots on the same side, again reflective of this, and then 2 little single electrons. And so again, right, that's starting to tell us how it's going to react and the power of that with these Lewis dot structures. And then so going back to nitrogen, you'd want to make a Lewis dot structure that reflects this. So 2 dots together for our paired dots in the S, then 1 dot on each side there.
Oxygen's negative, it's trying to fill the rest of the
Yeah,
shell.
exactly. So yeah, so you're starting to see that, right? So okay, oxygen's -2, right? Because it's missing 2, so it like literally needs 2 electrons, right? You can see the same thing. So nitrogen nitride, right, -3, needs 3 electrons.
So if there's a pair of
No.
So in the same sense that you have a magnet with a positive and a negative end, and you have atoms that have positive and negative spin charges. Like you have a magnet atom, for example, where the 2p orbitals are pointing the other direction. Does that change the properties of the atom?
I guess I'm not quite sure of your question, but like, yes, there are spin states, but I'm not sure they're like as influential as you're thinking. But let's talk after class, because I think that will go completely off topic. All right, so let's kind of continue with our periodic table filling in. So we were at the 1s, so we said, okay, we started our second energy level, 2s, 2p, right? So then neon is 2p6. So of course, satisfied by the octet rule. Now we start with sodium. So that starts our third energy level with our 3s. So of course, sodium, right, 3s1, magnesium 3s2. And then, oops, oh my gosh. And then aluminum, right, is 3p. So again, just filling that in. So argon, 3p6. And so then continuing, so then we have 4s. And so now we forgot about 3D, or rather they haven't come up yet. So let's look at this. And this kind of answers a previous question in the chat now. And so now that we're at the third energy level, so at the third energy level, now we have allowed s, p, and d orbitals. But if we look back, maybe at p table, so you can tell, right, it's a pretty small difference now already between the 4s and the 3d. So looking at that, that's why our 4s gets filled first, and then we go back to fill the 3d here. And again, you just follow in order so it matches with our periodic table. So yes, we're back at 3d here. Because that's where it's allowed. So it goes back to quantum mechanics, right? So we don't start at 1D because it's literally not allowed. Yeah, so that's where it's now allowed, right? So going back to the Bohr model, that's why you have 18. And so again, right, there was a 3s that was first. So again, just a bigger sphere. Then we had, right, our 3p's again, which again were just now bigger dumbbells. And then our d orbitals, there are 5 of them. I'll pull up a pretty picture. So usually I would draw d orbitals. I don't like these pictures. This is a good picture. And, oh, sorry, what is, oh, there we go. What are we showing? So this one's showing you all our orbitals. And so I like this picture because of the shading. So the shading matters. The other pictures that don't show you the shading is not as helpful for, again, later and for really appreciating and using the Lewis dot structure and these orbitals to their full power. And so again, appreciate the shading. So just kind of take it in for now. So 5d orbitals, so these are them. So, and they're labeled by, again, their axes. So we have dxy, so that's in the xy plane. Again, note the shading. dxz, so z is upright, so you can see this is in the xz plane. dz squared is this funny little donut one, is what people always say, right? You got like the dumbbell with the donut. But notice that the dumbbell has the same shading, right? So it's not like the dumbbell of the p orbitals where they have opposite shading. Yeah, so these are p orbitals, right? So this is what an s orbital looks like, so all same color. P's have opposite shading on each lobe, which again, we'll hold that thought of where that's going. And then again, there's D's, so dyz, obviously in the yz plane. And then the only funky one is this x squared minus y squared. And it's distinct in that it lies on the X and Y line. So all the others kind of lie between, but this one is actually on the X and the Y axes. So that gives it its character. The F orbitals are down here, but we'll save your excitement for a second. But back to our Ds, so right there are 5 of them, and they each hold 2 electrons, so 10 total in the Ds. So 5 orbitals, right, 2 in each, so 10. And so right, if you add up, so okay, well we said there were 2 in the S, 6 in the P, plus 10, so 2 plus 6 plus 10, that gives us 18 again. So if we go back right to the Bohr model, 18. And there is actually a formula that goes with this, so the number of electrons is 2n squared for each one of these. So you can see 3, so 3 squared times 2 is 18. So that's where that comes from. But I usually just kind of derive it. All right, so then back to our periodic table and filling in our electrons for our electron configuration. And so again, right, our D block is 10 long. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So perfect, so that matches. Let's see, let's look at, which one should we look at? Let's try the electron configuration. Let's do titanium and just see what we think. I said vanadium, right? I said titanium, whoops. All right, so what do we get for the electron configuration of titanium? So 3D2. But we need, so remember, we got to say more than that. So for the electron configuration, we should say the whole thing, or now is a good time to talk about the abbreviated method. Right, so we always start at the beginning. Yeah, so 1s, but how many are in the S? So 1s2, 2s2. Yep. Excellent. And so then the other trick is, so we could also abbreviate this by the previous noble gas. So if we look, so titanium, so the previous noble gas is argon. So the other way to write it is say, okay, in brackets argon, so basically, right, that means all of this. So starting with that electron configuration, and then 4s2, 3d2. So that looks good. That's about what we expect. And now let's look at chromium for a second. and look at its electron configuration. Or what you think it would be. Yeah. Yeah, go for it. Well, we can start at argon, and then,
The, argon 4s2, 3d4.
3d4. So did everybody get that? So let's make sure we at least got, so right, we're at 4s and 3d. 1, 2, 3, 4. And so what you might notice, though, okay, so if we look at that, what if we go check it with the periodic table? What, can you read that? Can you see what's funny? Yeah, it says 5, so I can't zoom in that well. And so it does kind of flag you as a warning of there's an exception. And let's at least kind of talk about why that exception is and then what I would expect on an exam, right? So for an exam, this would be fine, right? So we're just filling up normally, right? I'm not expecting you to start memorizing every single exception or anything. But on an exam, what I might do is say, hey, in actuality, you know, even though we expect it to be this, the chromium electron configuration is this. And so, right, we find, well, if we look it up, it's really argon 4s1, 3d5. And so your job is to then kind of explain why. And so let's look at that. And it all goes back to those little energy levels. So again, I like this picture. So we're looking, okay, again, they're really close, right? Our s and our d orbitals, so our 4s and our 3d. So they're pretty close in energy. And so that's what's going on. So again, we can kind of draw this out. So this is, again, what we expect. And so we can draw out, so our 4s, so it's sitting there with 2 happy electrons, and then our 3d. So again, there's 5 of them, 1, 2, 3, 4, 5. And then 1, 2, 3, 4. And so here we have, right, a little scenario. Well, what's happening is, so this energy gap between the 4 and the s must be pretty small, such that it's much more favorable, right, to promote this electron over here, so it can be by itself, and then that's going to make it happier. Right, so now we see our actual, right, 4s1, so now we have each one of those electrons in their own separate orbital, and so that is, again, more energetically favorable.
Because you don't expend energy because the opposite spin.
Right, yeah, so you're not expending that energy to force the pairing with the opposite spins, exactly, so this is more favorable. And it just kind of depends, right? So that's why I'm not like expecting you to kind of now go through and memorize every exception, because there are always exceptions, right? And that's what creates kind of cool reactivity and weird oxidation states for all these funky metals, right? Is because, okay, they can always throw their d orbitals around and do different things energetically. Yeah.
Does the electron state change at all with temperature?
Yes, it could. So, yeah, that's why we're not going to start going into all that right now. All right. Oh,
I have another question. So if they get closer and closer and closer, does this happen more and more the heavier you get?
yeah, so potentially, right? So that's why those other elements could be, you know, maybe more reactive. The other problem is, like, the heavier elements also get kind of more unstable.
Okay.
So, yeah, a quick note. So I'm trying to give you all a break, too, if I could pull it up. Because I wanted to show this little chart that I was looking at. So if you look at Wikipedia, and this is kind of cool, because it shows you the synthetic elements, right? Because we have a lot of elements that are only known synthetically. And so you can start getting into, like, what are stable, ratios too of like protons and neutrons, and then also like how many electrons, right, are stable as you go out and then start talking about like, theoretical orbitals. But then, right, also remember we have some radioactive elements that are just inherently unstable, especially again as we get to those heavier ones. So just kind of keep that in mind too, is like these heavier elements tend to also just be inherently radioactive or unstable, generally because of the proton neutron ratio. So something about that with those big elements, once it starts getting off, that makes it radioactive and they, start decaying. All right, yeah, let's take a quick break. So let's meet back in like 10 minutes, so like 12:10 roughly. Give me a second, like seriously.
So I think I see where this is going. So I have a couple examples here of why, because they want to fill or have, they want to have the octets, right? So NaCl, what sodium has this one sitting here, so it gives it to chlorine, which is missing one, right?
Yep.
And then oxygen and hydrogen would share.
Yeah, so that's what we'll get into is like,
That's what we're headed, is what I'm saying. But I think I'm starting to see the pattern.
yeah.
I'm just
good.
asking if that's correct.
Yeah,
Okay.
sorry, I'm gonna run. Yeah, I'll get the homework.
I think I'm getting it. It's just leaving. I really had to do some mental gymnastics to make the connections to chemical dots. So it's just like all kind of. Yeah, there's five.
That makes, okay, that's a little bit of a mix.
Yeah, that sounds like.
Okay.
And the number of feet doesn't matter. It's just telling you what energy it has. Because there's only going to be two pairs or one pair.
There's multiple energy levels. So you'll have.
But that doesn't matter. There's only one pair.
It's one, so each P has its own share. And it's three shell. So P3 has three, P4 has three total.
Three total.
I don't think it's pairs, because that's the one that looks like the dumbbell. I think it's three total.
Two. No. Because hydrogen is 1s1, one electron. And we go to helium, it's 1s2, so it's 2 electrons. So that's one pair.
That's the one pair for S. P still make pairs. I think the P is the weird one that doesn't pair. All the others do. Maybe it was three pairs. Oh, no, but it was three pairs.
Right, so it's
Yeah.
call me Walter White.
What I'm understanding is trying to see why some of these might make the two different types of issues, ionic versus because it wants to fill all of its shells, right? Or it wants to be. So if you have something like hydrogen, which has one share,
Don't want to take it.
oxygen. Hydrogen's the weird one. It's not part of, it's part of this group, but it shares, it only has one. So it shares with oxygen. Oxygen is the one that's It's something like sodium, which has one, has the two in the estrogen. So it just gives it like, to whatever the other one is. That's what I had to do.
That might have been the case.
I didn't see how it was understanding and like, wait, this is, oh.
Dude, I wonder if
If I understand chemistry better than physics, I don't
my high school principal had physics and I told him I was studying civil engineering. He's like, just be a chemical engineer. I'm like, no, I hate chemistry. But if I'm studying physics, it is hard.
Physics sucks. But it's so much fun. It's so interesting.
I wish I would have paid attention. I signed up for a reason. Broke my heart.
I messed up that one national.
Oh, that, oh, yeah.
We did that all the same day. We got out of class at like 4:20, then we went to like, right? Oh no, I'm so good.
I don't know if you should do it.
Well, to be fair, all I did was. I will make sure that
She gave me a B, bro. Yeah. On my, this is my final assignment for writing campaigns.
Right, yeah, one key.
Actually, the worst part is, I signed up for the class, and she did all online. The first video for introduction, she's like, hey guys, this is a business class. You should treat this like a job. You better your paycheck, you better be never come. And I was like, oh, dude. I did a couple of Zoom meetings, and she's like, yeah, I think a lot of these kids like this is what the real world is. And I was like, no, I understand that. It's a freshman level class. And why is it always the freshman level class?
So, yeah, I did one.
I barely passed my writing project in high school.
I know you know.
That's what I was telling you about the math teacher. That was my highest grade I got.
Yes, yes.
I will make sure you show.
Problem was I took algebra 2 when I was 17, and then I took calculus when I was 20 something, and I liked the calculus. So I had to go back and retake 95, 111.
I took EP calculus my sophomore year of high school. And I walked in and she was going through the material so fast. And I like math, not this
I mean, like a Christian consent. That doesn't make sense.
Oh, never mind.
I was in high school, international. But they didn't environmental science.
A lot of my friends were and then they all went to like South Africa. They all lived like that area, and I was like, I was in North Africa, so I socialized with a lot of like regular kids, and I was just like having fun.
Actually, I mean, there's a really weird dynamic because it's a really big.
Hi, first I was wondering if you post chapter 3,
Yeah, it should be under, I think it's under this week's notes, the live.
it's the live one.
Yeah, oh, maybe it's not visible.
Oh, yeah, because I saw the chapter 2 one, but not the chapter 3.
Yeah, because what happens is every time I post the link, it makes it hidden, even though it's like I'm posting it. Okay, yeah, it was hidden.
Oh, yay. All right,
Okay.
I just wanted to, yay.
Hi, I have a quick question. So,
Okay. All right, let's get started again. So I knew I forgot something in the welcome announcements. So I think something is wrong with the CHEM Ed. At least that's what the library had sent me on Friday, and they didn't update me. And a few people have been saying that they can't get to the journal articles. So is that true? Okay, so I guess today I will post the previous journal article, so for week 2. So I'll post that since we're having issues. So yeah, that'll be on Blackboard. So coming shortly. All right, so let's continue with our electron configuration. Where were we? All right, so we were filling in. So we had started the 4th energy level, but okay, we had to go back to our 3Ds. And then right on gallium, so okay, now we're back to 4p. And so the other way to kind of think about this is a coordinate system in some ways, right? So now we're at 4p1, 4p2, 4p3, 4, 5, 6 again. So of course, now we're at krypton. So 4p6. Do you have questions back there? You have a question? Do you have a question? There's a lot of talking, so I assume that you had a question that needed to be addressed. And so now we're at 5 here, so 5s. So again, right now we're at our 5th energy level. So we're just thinking with our onion shells. Now yttrium, so this is going to be 4d. So again, just write that right so we keep it straight. So again, Ds are allowed in our 4th energy level. Now filling this in, so of course, right, this completes our 4d10. Indium takes us back to 5p. Oops, sorry, over scrolling. So 5p, obviously xenon, 5p. So xenon, 5p6. And so now we go to cesium, so 6s, right? So 6s1, 6s2. Here's where things start to get funny again. And so we said, now we have to remind ourselves, well, back at the 4th energy level, so now let's go down. And so now that we're at the 4th energy level, now we can start having F orbitals. So right now what's allowed are S, P, D, and F. And so we can go back to the pretty picture people liked. And so for the record, I've never drawn out F orbitals in my life, and I don't anticipate needing to start doing that. And again, just at least appreciate the funky pictures, right? And we want to take away, there are 7 of them. 1, 2, 3, 4, 5, 6, 7. And same pattern, right? They can hold 2 electrons each. Now we can go back. So right, F orbitals, 7, 2 electrons in each. So then we get to 14 electrons total. And so then we can do our little trick again, where we count across, and this is where the discrepancies start. So what happens if you count across just here as drawn? So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's funky, right? That's a problem. And so what I like to do, and again, you may find different discrepancies, and so this is where they arrive from. But I would go ahead and put lanthanum back here. So lanthanum really starts 5D1. So that's 5D1, right? So we could do our electron configuration. And if we look, now I have too many tabs, at our P table, we see that this is reflected in the structure here, right? And it puts a little like errant message, but in my mind, this makes total sense, right? So we've filled up, again, starting back, so we're at 57 with lanthanum. So that means we can start with xenon, right? 54, just going back to our previous noble gas. So starting with that electron configuration, and then so I'll click on lanthanum, and then you can see 6s2, which agrees, and then again 5d1. And so what's kind of funny is this periodic table in the room does kind of reflect that. It has a bar here, so maybe that's helpful. Other periodic tables, actually this one, you can see how this one, for some reason, is trying to put lutetium over here, but I would disagree with that. Just again because of the electron configuration. So then we go over to cerium, and it again follows with how we're thinking about this. So cerium starts 4F1, and yes, we did fill in 5D1 first, so that is the electron configuration. And we can write that out. So again, cerium now starts 4F1 there. And again, I'll write this out just to be explicit. So again, cerium, right, electron configuration. And we'll start again at xenon. And so looking back at our periodic table, so xenon, then 6s2, then we do lanthanum, right, because we're just going in numerical order, so don't get lost. So 55, 56, 57, so that's, right, 6s2, 5d1, and then ending in that 4f1 for cerium. Does everybody follow that? And so let's continue the pattern. And so what we'll see is, again, right, kind of these exceptions, right? The electrons are going to kind of move around between the D and the F, kind of depending. So if we click on the next one, and I'm not quite sure how to pronounce this, so I apologize, but praseodymium. Yeah, praseodymium. So this element, right, now it's skipped over the D's, right? So it doesn't have 4 D's, so it's okay, again, for our purposes, because, so let's write, right, electron configuration. So this is okay. So we're going to say, right, this is fine. So for PR, this is again what we expect, right? So we just fill it in normally. So xenon, 6s2, 5d1, and then what we expect, again going over. So this is 4f1, so this should be 4f2. And again, what we care about, the most important thing, is that you have the correct total number of electrons. So we could start with xenon. So we're at 54 plus 2, 56, plus 3, 59, right? And that brings us to the correct number of electrons. So this is okay. But again, just like before, we'll see these exceptions as the electrons just kind of do what's more energetically favorable. And if you happen to just like know this one and know that, yes, that's the correct electron configuration, obviously I would also accept this answer on a test. So it at least has to be, reasonable, logical. And so we continue, and again, right, so a lot of these have skipped the D's, and then for some reason, this next element, gadolinium, has, right, 5d1, 4f7, probably, again, just to put one electron in each orbital. So just whatever is more energetically favorable. Well, let's take it to the end. So, okay, so now we're back at lutetium. And so, again, it does end up falling in with our thinking. So 5d1, then 4f14. And so now that we're at 71, now we can go back to hafnium. And so the most important thing now is to remember to at least put in the 4f14 somewhere, right? So that's all we're saying. So now we're at hafnium, right? Tantalum, tungsten. And the important thing is just to include all those F electrons that are in there. Does that make sense? And then it's kind of, again, more apparent. So now we're still back at 5d1, 2, 3, 4, et cetera there. No questions? Feeling okay about this? Yeah, question? Well, I would just, again, go with the pattern, right? 4F1, 4F2, 4F3. But then in actuality, right, they're going to feel funky because it's, again, just trying to minimize energy overall. Yeah, so, right, I would just fill it up with how we expect. Does that make sense? So then, right, this ends up being 4F14. Yeah. And it does end up following along. And we'll go back and do another F block practice in a second. I think there's still some questions, but let's finish out our periodic table. And so, okay, so now we're at mercury. So that concludes 5d10. So now we're back at 6p, right, at thallium. So 6p1, 2, 3, 4, 5, 6. So 6p6. And then again, right, things start to get funky. So 7s. So same thing, right? For our purposes, I put actinium up here. So now we're at 6d1. And we could see that is reflected, right, in the electron configuration here. So 7s2, 6d1. And then again, right, just continue filling. There are some exceptions, right? So notice thorium is 62 for some reason. Again, just whatever's favorable. And uranium goes back to kind of our expected pattern, right? So 61, 5F3. So that kind of falls in line there. And so again, lawrencium, so that ends our 5F14. And we can go back, and again, these are all unknown elements at this point, so this is getting crazy anyways. And now we go back, right, and fill in our last Ds, so fill up our 6 Ds, and now we're at 7p down at all these synthetic ones. All right, let's try the electron configuration. Let's do neptunium and see how it goes. So again, right, just do what we expect, then we can talk about any funky behavior. All right, who wants to try neptunium's electron configuration? All right, so let's start at our noble gas. So radon, so what's our symbol for radon? So Rn, and then 64, 5F1. So do people like this? So let's look at it. So we started at radon, right? So now we're here, and actually let me go to my annotated one. I didn't do this very smartly. So radon, so starting there, so 7s2, right? And then we said that this starts our 6d down here. So then 6d. Now this is where I think maybe something funky happened. Because what did other people, because right, we have our d here, so we should have 6d1, right? And then shouldn't we go down to 5f, 1, 2, 3, 4?
I was looking at the periodic table handout, and the actual electron configuration on the bottom of the element kept jumping around, so I wasn't too sure what it was.
Yeah, but just so filling it in, so let's go back and fix this answer, right? So we start 6d. Well, 6d, I would still put it as 1, right? Because we just want to fill up 1 for the actinum, right? And then it switches to the 5f.
Would it be 61, 5, 4?
Yeah, so that's what I would say, is 61, 5f4. So that would be better. And we could check it and see if that is real, and that does, again, happen to match, but again, we may not always expect that. But this is, right, the electron configuration, just kind of going and filling it in. And so does that answer your question on the F block? Or,
But, my other question is, on the F block, the lanthanides and actinides, that starts on row 4 and then goes to row 5, is that right, 5F?
yeah, so lanthanides, and again, what's confusing is I put lanthanum still in the D block, right? Even though it's called the lanthanides and actinides, yeah, it's electron configuration wise, it's the first one. So, right, lanthanum is 5D1, actinium is 6D1, and then we proceed, right? So it goes from 5D1 and then to 4F. So question in the chat, I guess I'm not sure what the question is. I'm confused why it's 61. So it's just 6D at this point because we're following the pattern, which I know isn't like the greatest explanation, but it's just kind of what we're doing, right? We're like building on energy levels. So we started at the 3D, right? Then you have the 4th energy level that has D orbitals. Then the 5th, which also has other ones, right? We go on to our theoretical ones. So now we have 5D here. So this is what's starting 5D. And so I think people are getting confused. So again, right, you just fill up the 1 on the D first, and then you have to start filling in the F orbitals. And this could be also a good time to show, because the other problem is we're trying to like look at this periodic table in like a better form. And so I don't know if it makes more sense to kind of try to look at it in this like expanded periodic table form. Because what we're saying is, right, at this point, well, now we have F orbitals, so we have to fill in, right, our F orbitals first. So this is kind of like our expanded periodic table view. So here's our lanthanides, actinides, so right, they're usually down at the bottom, but imagine if we could shove them in there. And so that's why, like, they've made the call of putting lutetium and lawrencium in here, and I think your book references a paper, so maybe we could look at that again. But again, I just kind of go off of what we expect for our electron configuration. All right. Any more questions on electron configuration? Let's do another practice. Yeah, what's your question?
It relates back to the temperature, and you're talking about, are there any orbitals or sites in other states of matter, like plasma and whatnot? Those sites like galactics or the atomic structures where they melt into something else?
I mean, maybe, but again, let's save those thoughts. So we're not skipping anything. So that's why I'm saying follow the numbers numerically, right? So we're at radon, 88. So we were at 7s2, 88. 89 is actinum. And so right now label that as 61. So it should kind of be here. 90 is thorium, right? And then, so label thorium as 5F1. So let's try bismuth, its electron configuration. Yeah.
Did you say there was an algebraic equation that kind of helps you like look at the electron configuration?
Oh, just for how many electrons are in each like main orbital, but not with each like atom. All right, who wants to give bismuth a shot? Still need more time, maybe. Anybody want to go for it? Yeah, where should we start at? So xenon. All right. Do people get this? What do we think about it? I see thumbs up. Yeah, Campbell.
Why would the E come before F? Like, wouldn't it, don't numerically, like, all the metanides come before, like, F and then, like, all the rest of them?
So this one, I won't be picky about what order you write it in, right? So if you wrote 6s2, 4f14, 5d10, 6p3, right, same thing. So yeah, I don't really care about the order as much. The main thing is, right, don't forget them. So as long as you have them, that's good. Because that's usually what people forget to do is either they leave out the F's or the D's or both. And again, right, sanity check. Let me pull up my calculator. So we started at xenon. So xenon's 54. Then we can add our little superscript. So plus 2, plus 10, plus 14, plus 3. And so 83. And yes, that matches with bismuth there. That always kind of your sanity check. And then always the other funky thing to kind of note is, right, when we kind of, again, talk about the Lewis dot structures and going back to how they behave, like for a lot of these, right, so for bismuth, we're mainly going to be looking at these, so for the valence electrons. And so again, right, just referring to kind of the families, and again, how it's going to have similar reactivity in a lot of ways to phosphorus, arsenic, and antimony. So again, that's just what we kind of expect there. So same thing, like again, like arsenic, you can kind of ignore all these D's, right? So we're just kind of treating it as 5 valence electrons, which again is reflected in the Lewis dot structure. All right, let's see. Are we okay? I know we didn't talk too much about balancing equations, but at least numerically, I think that should be okay. But if, again, if you need individual help, don't hesitate to ask me for help. But let's keep it moving for now. So I need to post the link to the chapter 4 live, so I'll do that. But again, right, I think we made the comment, so we're trying to figure out the whole electronic structure thing, right? And our book is trying to take us through this historical journey and, right, well, how do we get to our electronic shells if we didn't know about them? Again, it's easy for us to kind of look back and like, oh yeah, everything works out great. And so part of, that exploration was the ionization energy. And so let's just first define, well, what is ionization energy? And so ionization energy is just defined as the minimum energy required to remove an electron from an atom, or it could be an ion, right, especially as we go down to each subsequent energies, and this is in the gas phase. And so this is always an endothermic process, meaning that it requires energy input. And then, of course, again, we kind of know this now, looking back, but again, we'll see this kind of in the data that's reflected in your textbook and talk about that. But, right, we're going to see, okay, well, those valence electrons are the easiest to remove. And so first, let's just do our general equation. And so we can kind of simplify our ionization energy just by our general equation. And usually they just use a M to symbolize any atom. So it doesn't matter, but just kind of metal atom here plus our ionization energy, right, gives us a cation here. And so we want to figure out, and we should put plus our electron, obviously, that was ejected. And so ionization means that it flies off. And again, we'll talk about that coming up. So ionization is basically going to be when our electron goes to infinity. So we can hold that thought for a second, or at least for later. And so then kind of what it's showing, so this is again kind of the oversimplified view, but what we're going to be looking at in this class is again, right, every energy level and kind of where does that jump occur. And so this would be considered, right, the first ionization energy since we started off with a neutral, right, and ended up with one ion. So then second ionization energy would be then to remove the next electron. So this is starting with an M+1 ion, right? And then you add now your IE2, so this is second ionization energy. And then obviously now that gives us a 2+. And so we could keep going on and on and on, third, fourth, fifth.
Does that energy have to come in any specific form?
Well, I mean, so these are gas phase calculations, right? So it's just calculating the energy required to do that, right? So right now we're just trying to get into, again, the onion layers, right? And so with that, again, let's appreciate now the first ionization energy trends. And so let's, again, right, let's be very clear, we're only talking about the removal of one electron. And so right now we're appreciating, okay, their ionization energies, so we can start looking at different patterns. And so, of course, right, helium has a pretty high ionization energy. And we go back down to lithium, so that's relatively low. Next one, a little bit higher, right, then we have this kind of weird jump down, and it goes up and down. And then, right, okay, let's at least start picking out the big pieces. So first thing we can point out, obviously our noble gases have pretty high ionization energies. So that goes back to they're already happy, right? They don't want to be losing electrons. So there's that. Then we can also notice our alkali metal trends. So as we go down, what do you notice as we go down our periodic table about our ionization energies? So they're getting lower, so they're decreasing, right? So it takes less energy. And so how does that relate back to our onion shells and what we just talked about with our electron configuration? Why is that?
Just got one electron coming out that's physically distant from the rest of the electrons in the shell. And it's probably more
And then why does it get lower, though, as we go down the periodic table?
Because there's more energy flowing with electrons.
You're saying like the opposite thing, right? Because we're showing less energy, right? So it's taking less energy to ionize rubidium versus lithium, right? So why is that? No, we're still not thinking of all the little energy levels that we just went over. So what happens as we go down?
Oh, it gets closer and closer, the energy levels.
Well, the energy levels are closer and closer, but right, we're getting farther and farther out though from the nucleus, right? So you're further out from the nucleus, yeah.
There's more free spaces
Yeah, it's again more the distance, right? So we're still not thinking of our onion shells, right? So as we go down, so we had said, right, we added each subsequent level, right? 2s, 3s, 4s, 5s. But that little valence electron, right, it's getting further and further out. So the effective nuclear charge, and so I kind of tend to forget the exact formula, but essentially, right, the effective charge, or like your force, is equal to Q1 times Q2 over R squared. And so all we're trying to say is, right, well, here are your charges. And so as our charges get further out, though, then that force, right, this is really our force that we're measuring, right? Our force gets weaker and weaker, right? So it's held out there as we're down at rubidium. So it's way over there, so it has a much weaker effective nuclear charge, right? As it's way out there, so it's going to take less energy to kick off that valence electron. So we see that reflected there. So does that make sense? So again, we have to think about our onion rings, how, right, that's getting farther and farther out. So that goes back to the reactivity too, right? So that's why lithium just kind of gently fizzes in some water, and I promise you we will play with them in lab. And then, right, sodium is reactive, potassium is our limit, right? And then we said rubidium, cesium are in ampules because they're so reactive, right? And so we can see this then with our kind of general trends. So, right, we're seeing that. So our ionization energy decreases down the group. So again, right, that valence electron is further from the nucleus. That's the only place where we have our positive charge is in the nucleus. And so now let's look at this next thing. But we'll look at, again, some funkiness. And so it says, this comment, that our first ionization energy generally increases across the period. And, right, it brings up, again, the effective nuclear charge. So that's what we're talking about. And so let's dive into this a little deeper. And so again, we're going to compare our nitrogen and oxygen scenarios and carbon. So if we look at carbon, so right, 2p, 2s, so filling in, so carbon is, I'll just write its electron configuration, so 1s2, 2s2, 2p2. So then, right, I'm just showing the valence ones. All right. And so the point is, so we're filling in this 2p as we go across. And so we can see that. So carbon now to nitrogen. So let's compare. So now nitrogen, 2p. And so again, essentially what we've done is we added another negative electron at the same distance, right? So this is what we mean by effective nuclear charge increases. So we're filling up that same orbital, right? That's the same distance away. So, okay, we're increasing the charge, which essentially means, and again, I'm not trying to quantify it exactly. I'm just trying to give you the general idea. Okay, more electrons, again, means more charge. So now it's held tighter to the nucleus. And so we can see that, right? So as, again, we increase, obviously it takes more energy to kick it off. But now if you're looking and paying attention, well, the first thing you're going to notice is, well, there's a slight dip in oxygen, right? So what you just told me now was already broken. But let's explain why, right? So now let's look at the difference. So now we're looking at oxygen. So 2P, 2S. So I drew it in. Now looking at nitrogen versus oxygen, so what's kind of the difference between them? And what might account for this slightly lower ionization energy for oxygen? Yes. So do we see that? So notice, right, so oxygen has the paired electrons again. So, right, we started paying an energy price there. So now what's kind of happening, and you have to think about, again, the process of the ionization. So we can think about, well, what is it to lose an electron from nitrogen, right? Well, that's unfavorable. Versus, okay, well, we can lose an electron from oxygen. And yeah, okay, we have this whole effective nuclear charge deal. Yes, we did add another electron, so that does kind of add to our effective nuclear charge. But don't forget about that price that we paid, right? So again, with our repulsion created by the electrons. So in some ways, it's kind of happy to get rid of that. Like, hey, you know, I don't want you in my orbital, so yes. And so, right, again, we see that a slightly smaller ionization energy. So that's what accounts for that trend there. And then again, right, trend generally continues. So fluorine is, of course, right, back up with an extremely high ionization energy, which again, right, we can draw our little orbitals and understand that. And of course, fluorine is really, really close to filling an octet. So, and then neon, right, even higher there. All right, I think we have to end there, having too much fun with this. And so we'll continue with this, right? So we'll keep talking about these ionization energies. We'll look back at those log charts in your book, which I know some people find them mysterious, but we'll look at them, right? So we'll kind of deconvolute them and kind of try to extract the data. All right, I will see you all in lab. And then any last questions before I end the stream here?
I had a question about the lab. So for the, I don't know if I did the equation right. I haven't balanced it yet. But I just wanted to ask.
Calcium carbonate, it needs CaCO3, and then that'll help you balance.
Okay. Yeah, because I couldn't figure out, like, I couldn't balance it at all, so thank you.
Sorry, I just didn't get my first quiz.
Oh, yeah. Oh, if you didn't get your quiz, I'm sorry I didn't get to you, but come get it.
Alyssa.
Oh, last name?
Two quick questions. One is, I have some work that I haven't turned in yet. Is it okay if I turn it in this week, like either Thursday? Or
Yeah.
Okay, and second, really quick. I was just a little confused. How did you, like when we're doing BI, what like helped you decide that you would choose that?
So we always can use like the previous noble gas, but then when we get confused, right, I always look at the numbers. So it's like, okay, bismuth is 83, so now I'm kind of looking back. Well, radon's 86, so we can't use that, so then we're just forced to start with xenon, yeah.
Thank you.
I finished the intro quiz.
Oh, thank you.
Chapter 2.
Thanks. Last name?
Works.
Last. I feel like I should have known that.
Rate check.
Is now a good time to ask about some stuff I don't understand about the material?
It depends how extensive, because I do have to migrate to labs. So.
It's not very. First of all, okay, so the letters at the end, that's like the different, is that the different shells?
The letters at the end, sorry.
Like the
Oh,
S.
yeah, the S, yeah, those all correspond to like the orbitals.
What is the big number at the,
No, I don't have a stapler.
and what is the, what determines the big number at the left?
Oh,
of
so the big number corresponds to the energy levels. That's what I was saying, just kind of like write it, right, so that you
Okay.
know where you're at.
Okay, so this, and what about, is this the number of electrons?
Yeah, so that's the number of electrons, but it's also like, you know, if it's completely full, it's the max that should be in that shell, right? So that's why, you know, it's 1s2, because you have to fill up the S, and then same thing, 2s2, you have to fill it in. And then the max the P can have is 6, but obviously, right, we have to stop it.
Okay,
See the
thanks.
quiz? Oh, you need your quiz.
Thank you.